Hello, everyone. My name is Aaron, and my group's going to be talking to you about frequency filtering techniques. So, since we're talking about frequency filtering, I want to give a little overview about the Fourier series and the Fourier transform first, and then talk about the specific filtering of notch filtering and then optimum notch filtering. Okay, so starting with the Fourier series, Fourier showed that any function, any periodic function, that repeats itself, no matter how complicated it may look or appear, it can be represented with a sum of sines or cosines. And that sum of sines is just the sum of all the different frequencies, and it's multiplied by a coefficient. So if you look at this equation right here, you can see this first term right here it's what's called the DC term, the zero frequency, and then it's the sum of either the cosines and or the sines. So as a visual representation to show you, so here's just a simple graph of a periodic function in blue that repeats itself, and this red sine wave is the just the first frequency. Then you can see as we add more frequencies, second, third, and fourth, it'll start to recreate that blue periodic function. And I got more examples to show you. So here's an applet I found to illustrate the recreation of the periodic function. Here's the periodic function, and I'll start off with the square. And as I add frequencies, you'll see the frequencies pop up right here. As I add them, you'll see that it'll start to recreate the periodic function. So there's the first frequency, and as I keep adding frequencies, you'll see it'll start to recreate the function. And as the sum goes off to infinity, it'll pretty much match it, except for you'll get these rough edges in any of these corners right here. And here's just another example of another periodic function. It's called the sawtooth function. And as I add the sum up the frequencies up to infinity, you'll see it pretty much matches it, except for the corners that become rough. So again, here's another illustration of the square, and it's just one period, and you can see as it sums up all the odd frequencies from 1 to, it looks like, about 19, it goes from a regular sine to pretty much the periodic squarish function. And here's a animation of the sawtooth again. You can see they add this time all the frequencies from 1 to 20. So next we're going to talk about the Fourier transform, and this is important because when you have an image that has noise and you take the Fourier transfer of that image, it's going to give you a representation of all the frequencies that are in that image, and specifically in our case, it's going to give you a frequency of the noise, and it's going to show you the magnitude of the frequencies at any spot. So show you some examples first. So here's just a basic rectangle, and you'll see that the distance from this horizontal distance from the white to white here, and this greater distance here plays an important part on determining the magnitude for the Fourier transform. So here's a magnitude image of the same rectangle that I showed you, and you can see that the distance in the horizontal direction from here to here is greater, even though in the image I just showed you before, that the distance right here was smaller than the vertical distance. So it kind of has the opposite effect. You can see that the distance from each frequency in the vertical distance here is a lot closer as opposed to the horizontal distance. It's kind of opposite when you take the Fourier transform regarding the magnitudes. So again, here's another representation of that same rectangle. This plot right here shows that the function, that the rectangle function that I showed earlier, has a higher magnitude, at the horizontal frequencies than the vertical frequencies. It reflects that the horizontal cross sections are narrow pulses, and the vertical cross sections have broader pulses, and the narrow pulses have higher frequency content than the broad pulses. So here's another diagram to help show what I mentioned before about the frequencies. Here's the your initial frequency, the zero, the DC term, and this would be your first frequency, and then as the frequencies go out, they would just graph here, and this is just a representation of the spatial domain, spatial frequency. And in the Fourier transform, when you're plotting the frequencies in the spatial frequency, you will always see that it also plots a mirror reflection on this side. And I have another some more examples to show you coming up right after this, to show you what that the mirror image or the reflection of it is. So here's an example of an image, a brightness image to the left here, and it shows a sinusoidal brightness image, and to the right is its two-dimensional Fourier transform, presented here also as a brightness image. Every pixel of the Fourier image is a spatial frequency value. The magnitude of the value is encoded by the brightness of the pixel. So looking in the Fourier transform, there's a bright pixel at the center right here. That's what I said before about that's the zero frequency, the DC term, and it's flanked to the right and the left by two bright pixels on both sides of this center point right here, and those encode the sinusoidal pattern. The brighter the peak here in the original image, I'm sorry, the higher the contrast in this image determines the brightness of the pixel in the Fourier transform. And also lastly, since there's only one Fourier component in the original image, all other values in the Fourier image are zero, and they're all depicted by black in all this other space. That's why there's only one frequency here. So again, here's another example. There's another sinusoidal brightness image, this time with lower frequency because there's more space in between the frequencies, and it's again with its Fourier transform. Again, it has three peaks. The middle is again the DC term, and then it shows the representation of the first frequency, and on the opposite side it's mirror image. And in this time you could see that the frequencies are much closer to the DC term, and that's again going back to the original image because the periods take longer. That means it's going to be, since the distance here is longer, it's going to be closer in the Fourier transform. And you could see from the previous image, the frequencies are a lot closer to the DC term as opposed to the first image I showed you, where the periods are a lot closer and happening quicker than the frequency has a little bit more space between that DC term. Here's another brightness image, and this time the sinusoidal waves have been orientated in a more diagonal way, and you can see that it has the same pattern in the Fourier transform. The frequencies have then also been rotated to a diagonal pattern. And one more image to show you how the magnitude of the frequencies in the original image affects the distance in the Fourier transform. So you can see there's greater distance here as opposed to this last image, so that's why it's the initial frequency is a lot closer to the DC term as opposed to the last image where they're a little bit more spaced out. Now I just wanted to show you what the Fourier transform looks for a regular type of image that's not just sinusoidal waves. So here's an image of a person, and again there's the Fourier transform, and this shows all the frequencies starting from the DC term in the middle. And again it looks symmetric because it again, it plots the mirror image of all these frequencies. So now I can talk about notch filtering. Notch filters are used to remove repetitive spectral noise from an image. They're also like narrow high pass filters, but they notch out certain frequencies except for the DC term, and they attenuate selected frequencies in a certain neighborhood and leave other frequencies of the Fourier transform basically unchanged. And that's a really important part. So out of the Fourier transform, it just looks for certain spots in that Fourier transform and takes out certain little bright spots. So the notch filter rejects frequencies in predefined neighborhoods about the center frequency. And again, just to reiterate, due to the symmetry of the Fourier transform, notch filters must appear in symmetric pairs about the origin, unless the one exception is if the notch filter is located at the origin, and then it'll appear just by itself. So here you see the original image of a football, and it has periodic noise to it, and it's some type of interference picked up when from the camera or from something else when the picture was taken. So again, the notch filter is like a reject filter. The notch filter multiplies that particular frequency by 0, and it eliminates it from the Fourier domain. And you could see right here that it notched out these particular points. And again, it has the because the Fourier transform is a mirror image, you have to also do it on the other side. So these three, the same as these three. And you could see that it in the after doing the notch filter, it takes away most of the periodic noise from the original image. You can see a little bit on the outer edges, but right in the middle where the football is, you can see it's much more clear, and there's all that noise removed. And if you take a look at the Fourier transform after the notch filter, you could see there's little darker spots here where it was multiplied by 0 and the frequencies were basically removed. And here's the image of a clown image with again periodic noise kind of in a diagonal direction. In the Fourier transform, you can see the diagonal here, and you can see that it notched out these specific points right here, multiplied those frequencies by 0, basically eliminated the magnitudes there. You can see here, and it took out most of the noise. Again, in the center there's a little bit of noise on the edges, but compared to the first image, a lot of the noise has been reduced. And another example of this time a color image of some twigs and some leaves, and it's Fourier transform here, and you can see that it notched out these lines and a bunch of little sporadic points throughout each of these sections. And you can see this time in the filtered image, the image, as opposed to the original, all these vertical and horizontal lines from the noise, you can see they pretty much all been eliminated, and the picture looks a lot more clear and pretty much free of noise. So now I just want to quickly talk about optimum notch filtering. It's very similar and pretty much identical to notch filtering. The only thing is you're subtracting a weighted portion of the noise. So you're just taking a little portion of the noise instead of a whole bunch of noise. If you take too much, like in the notch filtering, you'll basically eliminate a lot of the information that you need from the original image. So here's what the equation looks like. Again, you're taking a notch filter and you're placing it over a part of the Fourier transform that has a peak, a bright spot, and instead of taking all of it out, you're taking just a weighted portion. So this is the noise and this is the weighted portion of the noise, and you're taking it from the Fourier transform, and that's how you get your new image. So the optimum filter basically removes a portion of the noise, not all of it, at a certain point